Since humanity first gazed upward into the darkness, stars have been our constant companions, our navigators, our calendar keepers, and our storytellers. Ancient civilizations saw heroes and gods painted across the night sky, while poets found metaphors for love and loss in their gentle light. Tonight, we embark on an extraordinary journey through billions of years, following the complete life story of stars from their quiet births in cosmic clouds to their spectacular or gentle deaths, and everything in between. Let's begin our journey in the vast stellar nurseries scattered throughout our galaxy and countless others across the universe. These regions, known as molecular clouds or stellar nurseries, are among the most beautiful and mysterious places in the cosmos. Picture, if you will, enormous clouds of gas and dust stretching across hundreds of light years, containing enough material to form thousands upon thousands of stars. These clouds are cold, incredibly cold, with temperatures hovering just a few degrees above absolute zero, that point where all molecular motion nearly ceases. In the darkness of space, these molecular clouds appear as great dark patches against the backdrop of distant stars, or when illuminated by nearby stellar light, they glow with ethereal beauty in shades of red, pink, and orange. The Eagle Nebula, the Orion Nebula, the Carina Nebula. These are just a few of the stellar nurseries we can observe from Earth, each one a birthplace of stars, a cosmic maternity ward where gravity slowly, patiently works its magic. The composition of these clouds tells the story of previous stellar generations. While hydrogen makes up about 74% of the mass, and helium about 24%, that remaining 2% contains heavier elements: carbon, oxygen, nitrogen, iron, and dozens of other elements forged in the hearts of stars that lived and died long before. This cosmic recycling means that every new star born carries within it the ashes of its ancestors, a beautiful continuity that connects all stellar generations across cosmic time. Within these molecular clouds, the gas and dust are not uniformly distributed. There are regions of slightly higher density, places where perhaps a passing shock wave from a distant supernova compressed the material just a bit, or where random thermal motions happen to bring more particles together. These density variations, though tiny at first, are the seeds from which stars will grow. It's remarkable to consider that such small irregularities, barely noticeable variations in the density of an already incredibly diffuse cloud, can eventually lead to the birth of objects as magnificent as stars. The process begins so gradually that if you could somehow watch it in real time, you would notice nothing happening for thousands of years. Gravity, that most patient of forces, begins to pull material toward these slightly denser regions. As more material accumulates, the gravitational pull becomes stronger, which in turn attracts even more material. It's a runaway process, but one that unfolds over timescales that dwarf human comprehension. We're talking about hundreds of thousands to millions of years just for this initial gathering phase. As the material begins to concentrate, something interesting happens to the cloud. The region that will become a star starts to rotate, slowly at first, almost imperceptibly. This rotation comes from the conservation of angular momentum, the same principle that causes a figure skater to spin faster when they pull their arms close to their body. As the cloud contracts, even the tiniest amount of initial rotation gets amplified. This rotation will eventually lead to the formation of a disk around the forming star, a disk from which planets may one day emerge. The temperature in the collapsing region begins to rise, though rise is relative when you're starting from near absolute zero. The gravitational potential energy of the falling material converts to kinetic energy, and collisions between particles convert that kinetic energy to heat. Still, for a very long time, this heat can escape easily. The cloud is still relatively transparent to infrared radiation, so the heat generated by the collapse radiates away into space. This is actually crucial for the star formation process to continue. If the heat couldn't escape, the pressure would build up and stop the collapse before a star could form. During this early phase, the collapsing cloud fragment might actually fragment further. Turbulence within the cloud, variations in density, and the complex interplay of magnetic fields can cause the original collapsing region to break apart into smaller pieces. This is why stars often form in groups or clusters rather than in isolation. Our own sun likely had siblings, stars that formed from the same molecular cloud about 4.5 billion years ago. These stellar siblings have long since dispersed throughout the galaxy, following their own orbital paths, but they all began their journeys together in the same stellar nursery. The magnetic fields threading through these molecular clouds play a fascinating and complex role in star formation. These fields can both help and hinder the process. On one hand, they can provide support against gravitational collapse, slowing down the star formation process. On the other hand, they can channel material along field lines, creating the beautiful pillar-like structures we see in images of star-forming regions. The interaction between gravity, rotation, turbulence, and magnetic fields creates a complex dance that determines not just whether stars form, but what kinds of stars form and how they're distributed. As we observe these stellar nurseries with our most powerful telescopes, we see them in different wavelengths of light, each revealing different aspects of the star formation process. In visible light, we might see dark clouds obscuring background stars. In infrared, we can peer through the dust to see the warm glow of forming stars hidden within. In radio wavelengths, we can detect the molecular signatures of various compounds in the cloud, not just simple molecules like molecular hydrogen and carbon monoxide, but complex organic molecules, the building blocks of life as we know it. The diversity of stellar nurseries across the universe is staggering. Some are relatively small and quiet, forming just a handful of stars over millions of years. Others are vast and active, forming thousands of stars in massive bursts of stellar birth. The Tarantula Nebula in the Large Magellanic Cloud, one of our galactic neighbours, is one of the most active star-forming regions known, creating massive stars at a prodigious rate. These different environments produce different populations of stars, from tiny red dwarfs that will shine for trillions of years to massive blue giants that will live fast and die young in spectacular supernova explosions. The conditions within a molecular cloud determine much about the stars that will form there. Temperature, density, chemical composition, turbulence levels, magnetic field strength. All these factors influence the initial mass function, the distribution of stellar masses that emerge from the cloud. This is one of the fundamental questions in astronomy. Why do stars form with the particular distribution of masses that we observe? Why are low-mass stars so much more common than high-mass stars? The answer lies in the complex physics of these stellar nurseries, in the interplay of forces and processes that we're still working to fully understand. As material continues to fall toward the centre of our collapsing cloud core, the density at the centre increases dramatically. We're transitioning now from a cold, diffuse cloud to something more concentrated, more defined. The central region, where most of the mass is accumulating, is becoming opaque to its own radiation. The heat generated by the continued collapse can no longer escape easily, and the temperature begins to rise more rapidly. We're witnessing the birth of what astronomers call a protostar. Not yet a true star, but no longer just a cloud either. The transformation from a collapsing cloud core to a protostar represents one of the most dramatic changes in the stellar evolution story. This nascent stellar object, still gathering material from its surroundings, still finding its equilibrium, is like a cosmic embryo developing within its protective cocoon of gas and dust. The protostar phase is dynamic, violent at times, yet it follows physical laws with mathematical precision. As the material continues to fall inward, the protostar grows in mass and temperature. The centre is now hot enough that the gas is partially ionized. Electrons are being stripped from their atoms by the intense collisions between particles. This ionization changes the opacity of the material, making it even harder for radiation to escape. The trapped radiation creates pressure, beginning to slow the collapse in the central regions while material continues to rain down from the outer envelope. Around the protostar, a remarkable structure begins to form, an accretion disk. This disk forms because of the conservation of angular momentum we mentioned earlier. As material falls inward, it cannot fall straight toward the centre if it has any rotational motion at all. Instead, it spirals inward, forming a flattened disk around the equator of the protostar. This disk is not passive. It's a dynamic, turbulent environment where material slowly spirals inward through a process called viscous accretion. The accretion disk is where planets will eventually form, but for now, it serves as a reservoir of material feeding the growing protostar. The inner edge of the disk is incredibly hot, heated by the friction of material spiraling inward and by radiation from the protostar itself. Temperatures here can reach thousands of degrees, hot enough to vaporize dust grains and even some rocky material. Further out in the disk, temperatures are cooler, allowing dust grains to survive and even grow through collisions and sticking. The protostar is now entering what astronomers call the class 0 phase, the earliest observable stage of stellar formation. At this point, most of the system's mass is still in the surrounding envelope, rather than the protostar itself. The protostar is deeply embedded in its natal cocoon, invisible to optical telescopes, but glowing brightly in the infrared as the heat from the accretion process warms the surrounding dust. One of the most spectacular phenomena during this phase is the emergence of bipolar outflows, jets of material shooting out from the poles of the protostar at tremendous speeds, sometimes hundreds of kilometers per second. These jets are thought to be driven by magnetic fields that thread through the accretion disk and channel material away from the protostar. It seems paradoxical. Here we have a forming star trying to gather material, yet it's simultaneously ejecting material at high speed. But these outflows serve a crucial purpose. They carry away excess angular momentum, allowing material in the disk to continue spiraling inward. Without this mechanism to remove angular momentum, the accretion process would slow or stop entirely. These protostellar jets can extend for light years, carving through the surrounding molecular cloud like cosmic blowtorches. When they slam into the ambient material, they create shock waves that heat and compress the gas, causing it to glow. These glowing regions, called Herbig hero objects after their discoverers, are signposts of star formation, visible evidence of the violent processes occurring as stars come into being. The timescale of the class 0 phase is relatively short by astronomical standards, perhaps 10,000 to 100,000 years, depending on the mass of the forming star. During this time, the protostar is gathering material at a prodigious rate, sometimes accreting the equivalent of Earth's mass in just a year. This rapid accretion generates enormous amounts of energy, making the protostar luminous, even though nuclear fusion has not yet begun in its core. As the envelope continues to fall onto the disk and protostar, the system gradually transitions to what astronomers call the Class 1 phase. Now more of the system's mass resides in the protostar than in the envelope. The envelope is becoming more transparent, allowing us to observe the protostar and disk more directly, though still primarily in infrared wavelengths. The accretion rate is beginning to slow, though material, is still falling onto the disk and being processed through to the star. During the class Y phase, which lasts perhaps 100,000 to a few 100,000 years, the protostar begins to develop more stellar characteristics. Its surface temperature rises, and it begins to develop the internal structure that will characterize it as a star. Deep in the core, temperatures are rising steadily, approaching but not yet reaching the threshold for hydrogen fusion. The protostar is supported against gravity not by fusion energy, but by the heat generated from continued accretion and from slow gravitational contraction. The accretion disk during this phase is a fascinating environment. Temperature gradients create different zones where different processes dominate. Close to the star, in the hot inner disk, only the most refractory materials can exist as solids. Further out, where temperatures drop below about 1,400 degrees Kelvin, silicate minerals can condense. Even further out, beyond what astronomers call the snowline, water ice can form. These different regions will eventually influence what types of planets can form where: rocky planets in the inner system, gas and ice giants further out. The disk is not smooth and uniform, but likely contains gaps, rings and spiral patterns. Some of these structures may be caused by forming planets, even at this early stage. Large dust grains are beginning to settle toward the midplane of the disk, creating a thin, dense layer where planet formation can begin in earnest. The process of growing from microscopic dust grains to planets is another epic story in itself, one that unfolds in parallel with the continuing evolution of the central star. As we move into the Class II phase, lasting perhaps 1 million to 10 million years, the protostar has accreted most of its final mass. The envelope has largely dissipated, either accreted onto the star and disk or blown away by stellar winds and radiation. Now we can see the young star directly in visible light, though it's still surrounded by its prominent disk. This is the stage we call a Tauri star, named after the prototype star Tauri in the constellation Taurus. Tauri stars are fascinating objects, showing all the signs of stellar adolescence. They're variable, their brightness changing on timescales of days to years. Some of this variability comes from hot or cool spots on the stellar surface, similar to sunspots but much larger and more dramatic. Some comes from uneven accretion, as clumps of material from the disk fall onto the star. Some may come from the star being periodically obscured by disk material or by planets forming within the disk. These young stars are also magnetically active, with magnetic fields thousands of times stronger than our Sun's current field. These powerful magnetic fields drive stellar winds and continue to power jets and outflows, though generally weaker than in earlier phases. The magnetic fields also channel material from the disk onto the star at specific locations, creating hotspots where the infalling material slams into the stellar surface. The Tauri phase is when planets are actively forming in the disk. Dust grains stick together to form larger particles. Those particles combine to form pebbles. Pebbles grow into boulders, boulders into planetesimals, and planetesimals into planets. It's a process fraught with collisions, some constructive, building larger objects, others destructive, grinding material back to dust. The gravitational influence of forming planets creates gaps and rings in the disk, structures we can now observe directly with our most powerful telescopes. During this time, the young star is still contracting slowly, its core temperature continuing to rise. For stars like our Sun, this pre-main sequence phase lasts about 50 million years. For more massive stars, it's much shorter, perhaps just a few million years or less. For the least massive stars, the red dwarfs, this phase can last hundreds of millions of years. The duration depends on how long it takes the core to reach the temperature and pressure needed for sustained hydrogen fusion. The The star's luminosity during the Tauri phase is actually higher than it will be during most of its main sequence lifetime. This seems counterintuitive. How can a star be brighter before fusion begins than after? The answer lies in the source of energy. The Tauri star is larger than its eventual main sequence size, with a lower surface temperature but a much larger surface area. The energy comes from gravitational contraction, the conversion of gravitational potential energy to heat as the star slowly shrinks. This slow contraction follows what's known as the Kelvin-Helmholtz timescale, named after Lord Kelvin and Hermann von Helmholtz, who first calculated how long the sun could shine by gravitational contraction alone. They got about 20 million years, which seemed impossibly long in the 19th century, but we now know is far too short for the sun's actual age. This calculation was one of the great puzzles of 19th century physics, resolved only with the discovery of nuclear fusion in the 20th century. As the Tauri star continues to contract, its core becomes denser and hotter. The temperature gradient from the core to the surface becomes steeper. Energy transport changes from primarily convective, where hot gas physically rises and cool gas sinks, to a combination of convection and radiation, where energy is carried by photons slowly diffusing outward. The star is developing the internal structure it will maintain for billions of years. Eventually, inevitably, the core temperature crosses a critical threshold, about 10 million degrees Kelvin. At this temperature, hydrogen nuclei are moving fast enough that when they collide, they can overcome their mutual electrical repulsion and get close enough for the strong nuclear force to bind them together. Nuclear fusion begins, not all at once, but gradually, as the fusion rate increases with rising temperature until it balances the energy being radiated from the star's surface. The ignition of hydrogen fusion in a star's core marks one of the most significant transitions in stellar evolution. This is the moment when a protostar truly becomes a star, when it joins what astronomers call the main sequence, that band on the Hertzsprung-Russell diagram where stars spend most of their lives steadily fusing hydrogen into helium. But this transition doesn't happen instantaneously. It's a gradual process, a careful balancing act between gravity trying to compress the star and radiation pressure trying to expand it. The fusion process that powers stars is remarkable in its elegance and complexity. In stars like our Sun, the primary fusion mechanism is the proton-proton chain. It begins with two hydrogen nuclei, single protons, colliding with enough energy to overcome their electrical repulsion. But even at 10 million degrees, such collisions rarely result in fusion. The protons need to get close enough for the weak nuclear force to convert one proton into a neutron, creating a deuterium nucleus, a positron, and a neutrino. This first step is the bottleneck of stellar fusion, occurring so rarely that a given proton in the Sun's core might wait billions of years before successfully fusing. Once deuterium is formed, the subsequent reactions happen much more quickly. The deuterium nucleus fuses with another proton to form helium-3, releasing energy in the form of a gamma ray. Then two helium-3 nuclei collide and fuse, producing helium-4 and releasing two protons back into the stellar core to participate in future reactions. The net result: 4 hydrogen nuclei have been converted into one helium nucleus, with the small difference in mass converted into energy, according to Einstein's famous equation. For more massive stars, those more than about 1 1/3 times the mass of our Sun, a different fusion mechanism dominates: the CNO cycle. This process uses carbon, nitrogen, and oxygen nuclei as catalysts, cycling through a series of reactions that similarly convert 4 hydrogen nuclei into one helium nucleus. The CNO cycle is much more temperature sensitive than the proton-proton chain, which is why it dominates in more massive stars with their hotter cores. As fusion begins to contribute significantly to the star's energy output, the star's structure begins to change. The energy generated in the core creates radiation pressure that opposes gravitational collapse. The star is searching for equilibrium, a balance point where the outward pressure exactly balances the inward pull of gravity. This balance, called hydrostatic equilibrium, is remarkably stable. If the star contracts slightly, the core temperature rises, fusion rates increase, generating more pressure that pushes the star back out. If the star expands slightly, the core cools, fusion rates decrease, and gravity pulls it back in. The approach to the main sequence follows different paths for stars of different masses. High-mass stars, those more than about 2 solar masses, contract relatively quickly and arrive on the main sequence still partially surrounded by infalling material. Their powerful radiation and stellar winds quickly clear away this remaining material, revealing hot blue stars that will dominate their stellar neighbourhoods with intense ultraviolet radiation. Solar mass stars, like our Sun, follow what's called the Hayashi track and then the Henye track, named after the astrophysicists who first calculated these evolutionary paths. During the Hayashi phase, the star is fully convective, with energy transported from core to surface by rising and falling gas currents. The star contracts at nearly constant surface temperature, becoming less luminous as its surface area decreases. Then as the core heats up, a radiative zone develops where energy is transported by photons rather than convection. The star now follows the Henye track, contracting at nearly constant luminosity while its surface temperature increases. Low-mass stars, those less than about half a solar mass, remain fully convective throughout their pre-main sequence evolution and indeed throughout their entire main sequence lifetime. This has profound implications for their evolution. In a fully convective star, material from throughout the star can be mixed into the core, providing fresh hydrogen fuel. This efficient mixing is one reason why low-mass stars can shine for such extraordinarily long times, trillions of years for the smallest red dwarfs. The arrival on the main sequence is not marked by any dramatic event. There's no stellar fanfare, no cosmic announcement. The star simply settles into a stable configuration where nuclear fusion provides all the energy being radiated from its surface. The star has found its equilibrium, a balance it will maintain for most of its lifetime. For our Sun, this happened about 4.5 billion years ago. For the most massive stars, this phase might have lasted only a few million years before they evolved beyond the main sequence. For the smallest stars, those with less than about 8% of the Sun's mass, the main sequence phase will last longer than the current age of the universe. The position where a star arrives on the main sequence depends almost entirely on its mass. This is the fundamental parameter that determines a star's destiny. Mass determines the core temperature and pressure, which determine the fusion rate, which determines the luminosity. More massive stars have higher core temperatures, faster fusion rates, and higher luminosities. They're the bright blue giants that dominate the night sky, despite being relatively rare. Less massive stars have cooler cores, slower fusion rates, and lower luminosities. They're the dim red dwarfs, invisible to the naked eye, but making up about 75% of all stars. This mass-luminosity relationship is remarkably steep. A star with twice the Sun's mass is not twice as luminous, but about 16 times as luminous. A star with 10 times the Sun's mass is about 10,000 times as luminous. This relationship has profound implications for stellar lifetimes. Even though massive stars have more fuel, they burn through it at a disproportionately faster rate. A star with 10 times the Sun's mass has 10 times as much fuel, but burns it 10,000 times faster, giving it a main sequence lifetime 1,000 times shorter than the Sun's. The newly arrived main sequence star is now in the prime of its life, steadily converting hydrogen to helium in its core, radiating energy into space, possibly warming planets, possibly enabling life. But even in this stable phase, changes are occurring. The composition of the core is slowly changing as hydrogen is converted to helium. The mean molecular weight of the core material is increasing, which means the core must contract slightly and heat up to maintain the same pressure. This gradual evolution means that stars slowly brighten over their main sequence lifetime. Our Sun is about 30% brighter now than it was when it first arrived on the main sequence. The internal structure of a main sequence star is beautifully organised into distinct zones. In the core, nuclear fusion generates energy. Surrounding the core is the radiative zone, where energy is transported outward by photons. These photons don't travel directly outward, but undergo a random walk, absorbed and re-emitted countless times. A photon generated in the Sun's core takes about 100,000 to 1,000,000 years to random walk its way to the surface, even though it's travelling at the speed of light between absorption events. Above the radiative zone in solar-type stars is the convection zone, where energy transport switches from radiation to convection. Here, hot gas rises to the surface, cools by radiating energy to space, and sinks back down to be reheated. This convection creates the granulation pattern visible on the Sun's surface, a constantly evolving pattern of rising hot gas and sinking cool gas. In more massive stars, the convection zone may be limited to the core region, while in less massive stars, convection extends throughout the entire star. The surface of a main sequence star, what we call the photosphere, is where the star transitions from opaque to transparent, where photons can finally escape to space. The temperature of the photosphere determines the star's colour. Hot stars appear blue or white. Cooler stars appear orange or red. Above the photosphere lies the stellar atmosphere, including the chromosphere and corona, regions of hot, tenuous gas shaped by the star's magnetic field. Main sequence stars are not static objects, but dynamic, ever-changing systems. They rotate, with different parts rotating at different rates. They have magnetic fields generated by the motion of electrically conducting gas. These magnetic fields create star spots, stellar flares, and coronal mass ejections. They pulsate, with some stars showing regular variations in brightness as they expand and contract. They lose mass through stellar winds, streams of particles flowing away from the star's surface. For stars in binary or multiple systems, which is actually the majority of stars, the main sequence phase can be complicated by interactions with companion stars. Mass transfer can occur if one star evolves and expands to fill its Roche lobe, the region where its gravity dominates. This can rejuvenate a star with fresh hydrogen fuel or strip away its outer layers, dramatically altering its evolution. Some of the most interesting and exotic objects in astronomy, X-ray binaries, cataclysmic variables, type Ia supernovae, result from the evolution of stars in binary systems. The main sequence phase represents the longest and most stable period in a star's life, a cosmic middle age where the star settles into a steady routine of converting hydrogen into helium. For our Sun, this phase will last about 10 billion years in total. We're currently about halfway through, with our star having spent 4.5 billion years on the main sequence and having about 5 billion years remaining before significant changes begin. This long duration makes the main sequence phase the defining chapter in most stars' stories. During this extended stable period, the star maintains a remarkable balance. Every second, the gravitational force trying to crush the star inward is precisely balanced by the pressure from hot gas and radiation pushing outward. Every second, The energy generated by fusion in the core exactly matches the energy radiated from the surface. This balance is self-regulating, maintained by feedback mechanisms that operate without any external control, a natural thermostat that keeps the star stable for billions of years. Let's delve deeper into what's happening inside a main sequence star during this phase. In the core, where temperatures exceed 10 million degrees, hydrogen nuclei are in constant motion, zipping around at speeds of hundreds of kilometers per second. The vast majority of collisions between nuclei don't result in fusion. The particles simply bounce off each other's electrical repulsion. But given the enormous number of particles and collisions, enough fusion reactions occur to power the star. The energy released by each individual fusion reaction is tiny, about 4 × 10 to the -12th joules, barely enough to make a speck of dust twitch. But the number of reactions is staggering. In our Sun's core, about 600 million tons of hydrogen are converted to helium every second. Of this, about 4 million tons of matter are converted directly into energy. Enough energy to power our entire civilization for millions of years, released every single second for billions of years. This energy begins its journey to the surface as high-energy gamma rays, but the path is far from straightforward. In the dense interior of the star, these gamma rays can't travel far before being absorbed by an atom. The atom then re-emits the energy, but not necessarily as a single gamma ray. It might emit 2 lower energy photons, or the energy might go into heating the surrounding gas, which then emits thermal radiation. Through countless absorption and re-emission events, the original gamma ray's energy is gradually degraded into many lower energy photons. The journey from core to surface is extraordinarily slow. In the radiative zone, photons undergo what physicists call a random walk. Each photon travels only about a centimetre before being absorbed and re-emitted in a random direction. It might go outward, inward, or sideways. The path of any individual photon is chaotic, unpredictable. On average, though, there's a slight bias toward moving outward, because the temperature gradient means photons are slightly more likely to be emitted outward than inward. This random walk means that energy takes an incredibly long time to escape from the star. If you could somehow tag a packet of energy created by fusion in the Sun's core right now and follow it on its journey, you would have to wait somewhere between 100,000 and 1,000,000 years before that energy finally reached the surface and was radiated into space. The sunlight warming your face today carries energy that was created when our ancestors were barely human, long before civilization, before agriculture, before language as we know it. In the outer portions of solar-type stars, energy transport shifts from radiation to convection. Here, the temperature gradient becomes so steep that radiation alone can't carry all the energy outward efficiently. The gas becomes unstable to convection. Hot gas bubbles up, while cooler gas sinks down, creating massive circulation cells that transport energy much more efficiently than radiation alone. These convection cells are visible on the Sun's surface as granulation, a pattern that looks like rice grains or cobblestones, each granule about the size of Texas, lasting only minutes before being replaced by new uprising gas. The magnetic field of a main sequence star plays a crucial role in its behavior and appearance. This field is generated by a dynamo process, where the motion of electrically conducting gas, the stellar plasma, generates electrical currents, which in turn generate magnetic fields. The combination of convection and rotation creates complex, twisted magnetic field configurations that thread through the star and extend far into space. These magnetic fields are responsible for much of the activity we observe on stars. Star spots, the stellar equivalent of sunspots, are regions where strong magnetic fields inhibit convection, creating cooler, darker areas on the stellar surface. Solar flares and stellar flares occur when twisted magnetic field lines suddenly reconfigure, releasing enormous amounts of energy in minutes or hours. The largest solar flares release as much energy as billions of hydrogen bombs. The stellar wind, a stream of charged particles flowing away from the star, is also shaped and accelerated by magnetic fields. For our Sun, this solar wind flows at speeds of 300 to 800 kilometers per second, carrying about 1 million tons of material away from the Sun every second. Over the Sun's lifetime, this adds up to a significant mass loss, though still only about 1/10,000th of the Sun's total mass. Different types of main sequence stars show remarkably different characteristics. The hot, massive O and B type stars are cosmic lighthouses, blazing with blue-white light, their surfaces exceeding 20,000 degrees Kelvin. These stars are so luminous that their radiation pressure drives powerful stellar winds, causing them to lose mass at rates millions of times faster than our Sun. They ionize vast regions of surrounding gas, creating the beautiful emission nebulae we see in star-forming regions. Moving down the main sequence, we find A-type stars like Sirius, the brightest star in our night sky. These stars, with surface temperatures around 10,000 degrees, appear brilliant white to our eyes. They're still quite massive and luminous, but not as extreme as their hotter cousins. Many A-type stars rotate rapidly, some spinning so fast that they're noticeably flattened at the poles and bulging at the equator. F-type stars, slightly hotter and more massive than our Sun, represent a transition zone. They're still white to our eyes, but with a hint of yellow. These stars often show interesting chemical peculiarities in their atmospheres, with unusual abundances of certain elements caused by the separation of elements through radiation pressure and gravitational settling. G-type stars like our Sun are yellow stars, though our Sun actually appears white from space. It only looks yellow from Earth's surface due to atmospheric scattering. These stars have surface temperatures around 5,700 degrees Kelvin and show the full range of magnetic activity: spots, flares, prominences, and coronal mass ejections. They're particularly interesting to us because they can support habitable zones at comfortable distances where liquid water can exist on planetary surfaces. K-type stars are orange stars, cooler and less massive than the Sun. They're particularly intriguing for astrobiology because they offer stable conditions for even longer than solar-type stars, potentially giving life more time to evolve. Their habitable zones are closer to the star, but they produce less harmful ultraviolet radiation than hotter stars. The smallest red dwarfs, those with less than about 35% of the Sun's mass, are perhaps the most remarkable stars in the universe in terms of longevity. These stars will shine for trillions of years, far longer than the current age of the universe. They burn their hydrogen fuel so slowly, so methodically, that they will still be shining long after our Sun has died, long after our galaxy has collided with Andromeda, perhaps even as the universe approaches its cold, dark final state. No red dwarf in the universe has yet evolved beyond the main sequence because the universe simply isn't old enough. The habitability of planets around main sequence stars depends on numerous factors beyond just being in the right temperature zone. The star's variability matters enormously. Young stars often experience powerful flares that could strip away planetary atmospheres or sterilize surfaces with radiation. The star's ultraviolet output affects atmospheric chemistry and the potential for complex molecules to form and survive. The stellar wind can erode planetary atmospheres over billions of years, especially for planets without protective magnetic fields. As main sequence stars age, subtle but important changes occur. The accumulation of helium in the core changes its structure and properties. Helium nuclei, with their 2 protons and 2 neutrons, are heavier than the hydrogen nuclei they replace. This means the core must contract slightly and heat up to maintain the pressure needed to support the overlying layers. As a result, the fusion rate increases gradually and the star slowly brightens. Our Sun demonstrates this gradual brightening beautifully. When life first emerged on Earth nearly 4 billion years ago, the Sun was about 70% as bright as it is today. This creates an interesting puzzle known as the faint young sun paradox. How could Earth have maintained liquid water and habitable conditions when the Sun was so much dimmer? The answer likely involves a thicker atmosphere with more greenhouse gases, though the exact details remain debated. This gradual brightening continues throughout the main sequence lifetime. In another billion years, the Sun will be about 10% brighter than today, enough to trigger a runaway greenhouse effect on Earth, boiling away the oceans and ending life as we know it. Venus may have experienced this fate already, transforming from a potentially habitable world to the hellish greenhouse we see today. The internal structure of main sequence stars evolves continuously, even though the changes are imperceptible on human timescales. The boundary between the core and the radiative zone gradually moves outward as more hydrogen is converted to helium. The convection zone depth changes with the star's evolving structure. Circulation patterns within the star adjust to the changing conditions, affecting everything from the star's rotation rate to its magnetic field generation. Different elements within the star follow different histories. While hydrogen is being destroyed in the core, converted to helium, the outer layers retain their original composition. This creates a composition gradient within the star, with helium-rich material in the core and hydrogen-rich material in the envelope. In fully convective stars, this gradient doesn't develop because material is constantly mixed throughout the star, but in stars with radiative zones, the gradient becomes pronounced over billions of years. The rotation of main sequence stars evolves over time as well. Young stars often rotate rapidly, spinning once every few days or even hours, but magnetic braking gradually slows them down. The stellar wind carries away angular momentum, and the magnetic field acts like a brake, coupling the wind to the star and transferring rotational energy into the wind's motion. Our Sun currently rotates once every 25 days at the equator and about 35 days near the poles. Yes, the Sun rotates differentially, with different latitudes rotating at different rates. This differential rotation is crucial for generating the Sun's magnetic field through the dynamo process. The combination of rotation and convection stretches and twists magnetic field lines, amplifying weak seed fields into the complex magnetic structures we observe. This dynamo process operates in cycles. Our Sun shows an 11-year cycle where the number of sunspots rises and falls, and the magnetic field completely reverses every 22 years. Binary star systems on the main sequence show fascinating additional phenomena. When two stars orbit close together, they raise tides on each other, just as the Moon raises tides on Earth, but much more extreme. These tides can synchronize the star's rotation with their orbital period, so they always show the same face to each other. They can transfer angular momentum between the star's rotation and their orbits. In very close binaries, the stars can even share a common envelope, creating contact binaries that look like cosmic peanuts. Mass transfer in binary systems can dramatically affect main sequence evolution. If one star evolves faster and begins to expand, it can transfer material to its companion. This can rejuvenate the receiving star with fresh hydrogen fuel, extending its main sequence lifetime. It can also spin up the receiving star to near breakup speed, creating rapidly rotating stars that wouldn't exist in isolation. Some of the most puzzling stars we observe, blue stragglers in star clusters for instance, are thought to result from such mass transfer or even stellar mergers. The environment around main sequence stars is constantly shaped by stellar radiation and winds. Any remaining protoplanetary disk material is gradually cleared away by radiation pressure and stellar winds. Planets migrate through gravitational interactions with disk material and with each other. Asteroids and comets are scattered by planetary gravity, some falling into the star, others ejected to interstellar space. The stellar radiation and wind create a bubble in the interstellar medium, a heliosphere or astrosphere that protects the planetary system from some interstellar radiation. For stars in clusters, the main sequence phase involves complex interactions with neighbouring stars. Close encounters can disrupt planetary systems, ejecting planets or sending comets raining down on inner worlds. The combined radiation from many hot stars can evaporate the atmospheres of nearby planets. The gravitational field of the cluster can strip away the outer portions of stellar systems, limiting how far from their stars planets can stably orbit. The chemical evolution of main sequence stars is subtle but important. While the core composition changes dramatically as hydrogen converts to helium, the surface composition can also evolve through various processes. In some stars, gravitational settling causes heavier elements to sink while lighter elements rise, creating unusual surface abundances. In others, convection dredges up processed material from deeper layers. Stellar winds preferentially remove certain elements. Accretion of interstellar material or planetary debris can alter surface composition. As billions of years pass on the main sequence, changes accumulate in the star's core that will eventually trigger a dramatic transformation. The helium produced by hydrogen fusion doesn't participate in the fusion reactions at main sequence temperatures. It requires much higher temperatures to fuse, so it simply accumulates in the core, an inert ash building up where once there was fuel. This helium core grows steadily larger and more massive as the star ages, until eventually a critical point is reached. When roughly 10 to 12% of the star's mass has been converted to helium in the core, hydrogen becomes depleted in the very centre. The core is now primarily helium, surrounded by a shell where hydrogen is still abundant enough to fuse. This marks the beginning of the end of the main sequence phase, and the start of one of the most dramatic transformations in stellar evolution, the expansion into a red giant. Without fusion occurring in the very centre, the helium core has no energy source to maintain its pressure against gravity. It begins to contract, slowly at first, then more rapidly. This contraction releases gravitational potential energy, heating both the core and the surrounding layers. The shell of hydrogen around the core, now heated to even higher temperatures than before, begins fusing at an accelerated rate. This shell burning is actually more vigorous than core burning was during the main sequence phase. Here's where stellar evolution becomes counterintuitive. You might expect that with the core contracting and heating up, the entire star would contract. But the opposite happens. The increased energy generation from shell burning heats the outer layers of the star, causing them to expand dramatically. The star begins to swell, growing larger and larger even as its core shrinks smaller and smaller. This is the beginning of the red giant phase. The expansion is truly remarkable in scale. Our Sun, currently about 1.4 million kilometres in diameter, will eventually expand to perhaps 200 times its current size, swallowing the orbits of Mercury and Venus, and possibly reaching Earth's current orbit. The exact size depends on various factors including mass loss through stellar winds, but the transformation from a modest yellow star to a bloated red giant is inevitable for stars like our Sun. As the star expands, its surface area increases dramatically, proportional to the square of the radius. Even though the star is generating more energy than before, this energy is spread over such a vast surface that the surface temperature actually decreases. The star's surface cools from nearly 6,000 degrees to perhaps 3,000 degrees, shifting its colour from yellow through orange to deep red. This is why we call them red giants. They're gigantic and red. The internal structure of a red giant is remarkably different from a main sequence star. The core, now made of helium, continues to contract and heat up, but hasn't yet reached the temperature needed for helium fusion, about 100 million degrees. Surrounding this inert core is a thin shell where hydrogen fusion occurs at a furious rate. Above this is a vast envelope of hydrogen-rich material, expanded to enormous size and held only tenuously by the star's gravity. The timescale for this transformation varies with stellar mass. For a star like our Sun, the expansion from main sequence to red giant takes a few 100 million years, brief compared to the 10 billion years spent on the main sequence. More massive stars evolve more quickly, completing the transition in just millions of years. Less massive stars take longer, but even they complete the transformation in less than 1 billion years. During this expansion phase, the star's luminosity increases dramatically, perhaps by a factor of 1,000 or more. A red giant version of our Sun will be about 2,000 times more luminous than it is today, even though its surface is much cooler. This increased luminosity comes from the enormous surface area. What the star lacks in surface temperature, it more than makes up for in size. The outer layers of a red giant are so distended, so far from the centre of gravity, that they're only loosely bound to the star. The surface gravity of a red giant is typically hundreds of times weaker than the Sun's current surface gravity. This weak gravity, combined with the high luminosity, drives a powerful stellar wind. Red giants lose mass at rates millions of times faster than the current solar wind, shedding a significant fraction of their total mass during this phase. This mass loss has profound implications for the star's future evolution and for the enrichment of the interstellar medium. The material blown off in the stellar wind is enriched with elements created during the star's lifetime: carbon, nitrogen, oxygen, and heavier elements produced through various nuclear processes. This material will eventually be incorporated into new generations of stars and planets, continuing the cosmic cycle of element enrichment. The convection zone in a red giant extends much deeper than in a main sequence star, reaching down almost to the hydrogen-burning shell. These deep convection zones can dredge up material that has been processed by nuclear reactions, bringing it to the surface where we can observe it. This first dredge-up event changes the surface composition of the star, increasing the abundance of helium and nitrogen while decreasing the abundance of carbon and oxygen. Red giants often show variability in their brightness. Some pulsate regularly, expanding and contracting with periods of days to years. These pulsations are driven by the same mechanism that drives Cepheid variables, the ionization and recombination of helium in the star's outer layers creates a valve mechanism that alternately traps and releases radiation, driving the pulsations. Other red giants show irregular variations caused by convection cells so large they significantly affect the star's total light output. As the helium core continues to contract and heat up, it eventually becomes electron degenerate. This is a quantum mechanical state where electrons are packed as closely together as the laws of physics allow. In this state, the pressure depends only on density, not temperature. The core becomes incredibly dense. A piece the size of a sugar cube would weigh as much as a car. This degenerate core continues to grow as shell burning adds more helium ash to it. For stars like our Sun, the helium core eventually reaches a critical mass of about 0.45 solar masses. At this point, the core temperature finally reaches the 100 million degrees needed for helium fusion. But because the core is degenerate, something dramatic happens. In normal matter, when fusion begins and releases energy, the material heats up and expands, naturally regulating the fusion rate. But degenerate matter doesn't expand when heated. The pressure is determined by quantum mechanics. not temperature. This leads to a runaway situation called the helium flash. When helium fusion begins in the degenerate core, the temperature rises, which increases the fusion rate, which raises the temperature further, creating an explosive feedback loop. Within seconds, the core is generating energy at a rate of about 100 billion times the Sun's current luminosity, briefly matching the power output of an entire galaxy. This enormous energy release finally heats the core enough to remove the degeneracy, allowing it to expand and return to normal behaviour. Remarkably, this dramatic event deep in the star's interior is almost invisible from the outside. The energy is absorbed by the overlying layers, causing some structural readjustment but no dramatic brightening. An observer watching the star would see it become slightly less luminous and slightly hotter as it settles into its new configuration, now fusing helium in its core and hydrogen in a surrounding shell. For more massive stars, those more than about 2 solar masses, the helium core never becomes degenerate. The core reaches helium fusion temperature while still behaving as an ideal gas, so there's no helium flash. The transition to core helium burning is smooth and gradual. These stars evolve somewhat differently, becoming supergiants rather than regular giants, with even more extreme properties. The red giant phase profoundly affects any planetary system around the star. Inner planets are either engulfed by the expanding star or subjected to such intense radiation that their surfaces are completely transformed. Rocky planets might have their surfaces melted into magma oceans. Atmospheres are stripped away by the intense stellar wind. Outer planets, previously frozen, might warm enough for liquid water to exist on their surfaces or on their moons, creating temporary habitable zones far from where life could have existed during the main sequence phase. For planets that are engulfed by the expanding star, their fate depends on their mass and composition. Small rocky planets are likely vaporized completely, their material mixed into the star's envelope. Larger planets, especially gas giants, might survive the engulfment, spiraling slowly inward through the star's envelope. This process, called common envelope evolution, can dramatically alter both the planet's orbit and the star's evolution. The red giant phase also affects the star's rotation and magnetic field. As the star expands, conservation of angular momentum causes it to rotate more slowly, just as a spinning ice skater slows down when extending their arms. The changing internal structure alters the dynamo process that generates magnetic fields. Some red giants show evidence of strong magnetic fields and stellar spots, while others appear magnetically quiet. Binary star systems show particularly interesting evolution during the red giant phase. If the stars are close enough, the expanding red giant can fill its Roche lobe, the region where its gravity dominates. Material then flows from the giant to its companion, creating an accretion stream and possibly an accretion disk around the companion. This mass transfer can dramatically alter the evolution of both stars, potentially creating exotic objects like blue stragglers, barium stars, or symbiotic variables. With helium fusion now occurring in the core, the star enters a new phase of nucleosynthesis, creating elements heavier than helium for the first time. This process, occurring deep within red giants and supergiants across the universe, is responsible for creating much of the carbon, oxygen, and other elements essential for life as we know it. The star has become a cosmic alchemist, transforming simple hydrogen and helium into the building blocks of planets and living organisms. The primary helium fusion process is the triple alpha reaction, where 3 helium-4 nuclei combine almost simultaneously to create carbon-12. This reaction requires such precise conditions that it almost seems designed to work. The process depends on a remarkable coincidence. Carbon-12 has an energy level almost exactly matches the combined energy of 3 helium nuclei at stellar temperatures. This resonance, predicted by astronomer Fred Hoyle before it was experimentally confirmed, greatly enhances the reaction rate. Without this coincidence, carbon would be extremely rare in the universe, and carbon-based life as we know it could not exist. The triple alpha process is incredibly temperature sensitive, proportional to temperature to the 40th power. This extreme sensitivity means that small changes in core temperature produce enormous changes in energy generation. A 1% increase in temperature produces a 40% increase in energy output. This sensitivity helps regulate the star's structure, but also makes helium burning less stable than hydrogen burning. Once carbon is produced, additional helium nuclei can fuse with it to create oxygen-16. This reaction competes with the triple alpha process, and the balance between them determines the carbon-to-oxygen ratio in the stellar core. This ratio is crucial for the star's later evolution and for the composition of the white dwarf that will eventually remain. The exact ratio depends sensitively on the reaction rates, which are still being refined by nuclear physicists. As helium burning proceeds, the core develops a complex structure. The very center becomes depleted of helium, building up carbon and oxygen ash. Surrounding this is a helium-burning shell, and outside that, the hydrogen-burning shell continues to operate. The star now has 2 distinct energy sources, each contributing to the total luminosity. This dual-shell burning configuration is less stable than single-core burning, leading to various instabilities and mixing episodes. For stars massive enough, the story doesn't end with carbon and oxygen. When the core temperature exceeds about 600 million degrees, carbon itself begins to fuse. Carbon fusion produces neon, sodium, and magnesium through various reaction channels. The process releases energy, but also produces copious neutrinos, ghostly particles that escape directly from the stellar core, carrying away energy and affecting the star's evolution. At even higher temperatures, around 1 billion degrees, neon burning begins. Neon-20 absorbs a high-energy photon and splits into oxygen-16 and helium-4. The helium can then fuse with remaining neon to produce magnesium. This photodisintegration process seems counterproductive, breaking apart nuclei that were previously built up. But it's part of the complex network of reactions that produce the variety of elements we observe. Oxygen burning, beginning around 1.5 billion degrees, produces a variety of elements, including silicon, sulfur, argon, and calcium. The reaction network becomes increasingly complex, with hundreds of different nuclear reactions occurring simultaneously. The star's core becomes a nuclear furnace of incredible complexity, with reaction chains branching and merging in an intricate dance of creation and destruction. The final stage of fusion in massive stars is silicon burning, occurring at temperatures exceeding 3 billion degrees. This process is different from previous burning stages. Rather than direct fusion of silicon nuclei, the process involves the photodisintegration of silicon into helium nuclei, which then gradually build up iron peak elements through a series of captures and decays. The end product is primarily iron-56 and nickel-56, the most tightly bound nuclei in nature. Iron represents a dead end for fusion reactions in stellar cores. Fusing iron nuclei to create heavier elements requires energy input rather than releasing energy. The star has reached the end of its ability to generate energy through fusion. For massive stars, this marks the beginning of the end. Core collapse and supernova explosion are imminent. But even for less massive stars that never reach iron production, the creation of elements continues through different processes. Throughout the red giant and supergiant phases, another crucial process of element creation occurs: slow neutron capture, or the S process. This happens when neutrons produced as byproducts of various fusion reactions are captured by atomic nuclei. The neutron capture is slow compared to radioactive decay, meaning that if an unstable nucleus is created, it typically decays before capturing another neutron. This process creates about half of all elements heavier than iron, following a specific path through the chart of Nucleosynthetase. The S process occurs primarily in the helium-burning shells of red giants, where carbon-13 serves as a neutron source. Carbon-13, created earlier when hydrogen burning converts carbon-12 to nitrogen-14 and then back to carbon-13, reacts with helium-4 to produce oxygen-16 and a free neutron. These neutrons then interact with iron seed nuclei, gradually building up heavier elements like strontium, barium, and lead. The efficiency of the S process depends on the neutron density and the amount of iron seed nuclei available. In metal-poor stars with less initial iron, each iron nucleus captures more neutrons on average, producing a different distribution of heavy elements than in metal-rich stars. This creates distinct signatures in stellar spectra that tell us about the conditions inside these stellar element factories. During certain phases of evolution, particularly during thermal pulses in asymptotic giant branch stars, the products of nucleosynthesis can be brought to the stellar surface through convection. These dredge-up events enrich the stellar atmosphere with carbon, S-process elements, and other products of nuclear burning. Some stars become so enriched in carbon that they transition from oxygen-rich to carbon-rich, dramatically changing their spectral appearance and the types of molecules that form in their atmospheres. The elements created in stellar cores don't immediately benefit the universe at large, they're locked deep within the star. But stellar winds, particularly during the red giant phase, gradually release some of this enriched material into space. Mass loss rates increase as stars evolve, with some stars losing more than half their mass during the giant phase. This gentle release of enriched material is one way stars contribute to the chemical evolution of galaxies. The temperature and density conditions in different stellar layers create a stratified element distribution. Hydrogen dominates the envelope. Helium is enhanced in regions that have experienced hydrogen burning. Carbon and oxygen accumulate where helium has burned, and heavier elements concentrate in the hottest, densest regions. This onion-like structure becomes more pronounced in massive stars with distinct shells of different composition surrounding an iron core. The nuclear reactions in stars don't just create elements, they also produce various isotopes of each element. For example, carbon exists primarily as carbon-12, but stars also produce carbon-13 and carbon-14. Oxygen has 3 stable isotopes, 16, 17 and 18, produced in different proportions by different processes. These isotopic ratios provide fingerprints of the nuclear processes that created them, allowing us to trace the origins of material in meteorites, planets, and even our own bodies. The energy generation from these various fusion processes follows different patterns than hydrogen burning. Helium burning produces about 1/10 the energy per unit mass as hydrogen burning. Carbon burning produces even less, and the energy yield continues to decrease for heavier elements. This means that each successive burning stage is shorter than the last. While hydrogen burning lasts billions of years, helium burning lasts millions of years, carbon burning thousands of years, and silicon burning just days. Neutrino losses become increasingly important as stellar cores heat up. These ghostly particles, produced in various fusion reactions and thermal processes, escape directly from the stellar core without interacting with the overlying material. At high temperatures, neutrino losses can exceed the energy carried away by photons. This energy drain accelerates stellar evolution, particularly in the late stages when core temperatures exceed billions of degrees. For stars like our Sun, those with initial masses less than about 8 times the solar mass, the end comes not with a bang, but with a whimper, though it's a beautifully spectacular whimper that creates some of the most stunning objects in the night sky. These stars lack the mass to continue nuclear fusion beyond helium burning, or in some cases carbon burning, and their deaths unfold through a series of gentle expulsions that return much of their material to space while leaving behind a dense, Earth-sized remnant. After the helium flash and the establishment of core helium burning, the star settles into a period of relative stability, fusing helium into carbon and oxygen in its core while continuing to burn hydrogen in a surrounding shell. This phase, called the horizontal branch phase, lasts about 100 million years for a solar mass star, much shorter than the main sequence phase, but still a significant period. The star is somewhat smaller and hotter than it was as a red giant, appearing orange or yellow rather than deep red. But helium fuel in the core is limited, and fusion consumes it relatively quickly. When the central helium is exhausted, the star faces another crisis. The core, now composed primarily of carbon and oxygen, begins to contract again. Without the mass to reach carbon fusion temperatures, this core will never again generate energy through fusion. It contracts and heats up, but not enough to ignite the next stage of nuclear burning. The star has reached a fundamental limit imposed by its mass. Around this inert carbon-oxygen core, helium burning continues in a shell, and further out, hydrogen burning continues in its own shell. The star now has 2 shell sources, an inherently unstable configuration. The star begins to expand again, becoming even larger than during its first red giant phase. This is the asymptotic giant branch phase, named because on stellar evolution diagrams, these stars approach, asymptote 2, the path they followed as first ascent red giants. The asymptotic giant branch, or AGB phase, is characterized by dramatic instabilities and mass loss. The dual shell sources create a situation where the star undergoes thermal pulses, periodic explosions in the helium-burning shell. Here's what happens. The hydrogen-burning shell steadily adds helium to the layer below. When enough helium accumulates, it suddenly ignites in a helium shell flash, far less dramatic than the core helium flash, but still significant. This pulse of energy pushes the hydrogen shell outward, temporarily extinguishing hydrogen burning. These thermal pulses occur every 10,000 to 100,000 years, depending on the star's mass. Each pulse drives convection that can reach from the helium-burning shell all the way to the stellar surface, dredging up freshly created carbon and S process elements. This third dredge-up enriches the stellar atmosphere with the products of nucleosynthesis, sometimes so dramatically that the star transitions from oxygen-rich to carbon-rich, becoming a carbon star with a distinctive red colour and molecular spectrum. The combination of high luminosity, low surface gravity, and thermal pulses drives extreme mass loss during the AGB phase. These stars shed material at rates that can exceed 1/10,000,000th of a solar mass per year. That might sound small, but it means losing an Earth mass of material every few years. The expelled material forms an expanding shell around the star, often visible as a detached shell in infrared observations. This expelled material is rich in dust grains that condense in the cooling outflow. In oxygen-rich stars, the dust is primarily silicates, the same minerals that make up much of Earth's crust. In carbon-rich stars, the dust includes graphite, silicon carbide, and possibly even tiny diamonds. These dust grains are crucial for the chemistry of interstellar space and eventually become incorporated into new planetary systems. The stardust grains found in primitive meteorites identified by their unusual isotopic ratios, were formed in the winds of dying AGB stars billions of years ago. As mass loss continues, the star's envelope becomes progressively thinner. The star is literally evaporating into space, gentle stellar winds carrying away its outer layers. Eventually, so much mass is lost that the envelope becomes transparent and we can see down to the hot interior. The surface temperature begins to increase even as the star continues to lose mass. The star moves across the Hertzsprung-Russell diagram from the cool red giant region toward the hot blue region. When the envelope mass drops below a critical value, something remarkable happens. The hot core, now exposed or nearly exposed, begins to ionize the previously expelled material. Ultraviolet photons from the hot stellar remnant excite the gas in the expanding shell, causing it to fluoresce. A planetary nebula is born, one of the most beautiful phenomena in astronomy. The name planetary nebula is a historical misnomer. When William Herschel first observed these objects in the 18th century, they appeared as small, round, greenish disks in his telescope, reminiscent of the planet Uranus, which he had recently discovered. We now know they have nothing to do with planets, but are instead the glowing shells of gas expelled by dying stars. Planetary nebulae come in an astounding variety of shapes and colours. Some are nearly perfect spheres, others are bipolar with two lobes extending in opposite directions. Some show intricate knots and filaments, others display multiple shells from different mass loss episodes. The shapes are determined by the star's rotation, magnetic fields, binary companions, and the interaction between fast and slow stellar winds. The colours come from different elements glowing at characteristic wavelengths: hydrogen red, oxygen green and blue, nitrogen red, helium blue. The central star of a planetary nebula is the exposed core of the former giant star, now evolving toward its final state as a white dwarf. This stellar remnant is incredibly hot, with surface temperatures that can exceed 100,000 degrees, hotter than almost any other stars in the universe. But it's also tiny, typically Earth-sized, so despite its high temperature, its total luminosity is modest. The star is supported not by fusion, but by electron degeneracy pressure, the quantum mechanical resistance of electrons to being squeezed too closely together. The planetary nebula phase is brief by astronomical standards, lasting only about 10,000 to 20,000 years. During this time, the nebula expands at speeds of 20 to 30 kilometers per second, growing ever larger and fainter. Eventually, the nebula becomes so large and diffuse that it fades from visibility, merging with the general interstellar medium. The beautiful glowing shell that announced the star's death dissipates into space, enriching the galaxy with heavy elements. Meanwhile, the central star continues to evolve. With no energy source beyond its stored heat, it simply cools and fades. The star contracts slightly until electron degeneracy pressure completely supports it, then maintains essentially the same size forever. A typical white dwarf has a mass of about 0.6 solar masses compressed into a volume the size of Earth. The density is staggering. A teaspoon of white dwarf material would weigh as much as a car. The composition of a white dwarf depends on the evolutionary history of its progenitor star. Most white dwarfs are composed primarily of carbon and oxygen, the ashes of helium burning. Some lower mass stars may produce helium white dwarfs if they lose their envelopes before helium burning begins. More massive progenitors might produce oxygen neon white dwarfs. The surface layer is typically a thin atmosphere of hydrogen or helium, the lightest elements floating to the top in the intense gravitational field. White dwarfs are supported by a remarkable quantum mechanical effect. The electrons in the white dwarf are packed so tightly that they become degenerate. Their quantum mechanical wave functions overlap, and they must obey the Pauli exclusion principle, which states that no two electrons can occupy the same quantum state. This creates a pressure that depends only on density, not temperature, allowing the white dwarf to support itself even as it cools toward absolute zero. There's a maximum mass that a white dwarf can have, known as the Chandrasekhar limit, about 1.4 solar masses. Above this mass, electron degeneracy pressure cannot support the star against gravity, and it would collapse to a neutron star or black hole. This limit has profound implications for stellar evolution and for the use of Type Ia supernova as cosmic distance indicators. The cooling of white dwarfs follows a predictable pattern that makes them useful as cosmic clocks. Young white dwarfs are hot and blue-white, but as they radiate away their thermal energy, they cool and fade, becoming yellow, then orange, then red, and eventually black, though this final stage takes longer than the current age of the universe. By measuring the temperature and luminosity of white dwarfs in star clusters, astronomers can determine the age of the cluster. The spectrum of a white dwarf tells fascinating stories about stellar death and sometimes stellar resurrection. Some white dwarfs show evidence of planetary debris falling onto their surfaces, the remnants of planetary systems that survived the star's red giant phase, only to be disrupted when orbits became unstable. These polluted white dwarfs give us a unique opportunity to study the composition of exoplanetary material. In binary systems, white dwarfs can have more dramatic futures. If a white dwarf has a close companion star, it can accrete material from that companion. If the accretion rate is just right, hydrogen can build up on the white dwarf's surface until it ignites in a thermonuclear runaway, creating a nova explosion. The white dwarf survives this explosion and can undergo multiple nova events over millions of years. If the white dwarf accretes enough material to approach the Chandrasekhar limit, something even more dramatic occurs. The entire white dwarf undergoes thermonuclear disruption in a Type Ia supernova, one of the most luminous events in the universe. These explosions are so uniform that they serve as standard candles for measuring cosmic distances, leading to the discovery that the universe's expansion is accelerating. The journey from main sequence star to white dwarf represents a remarkable transformation. A star that once fused hydrogen into helium across millions or billions of years becomes a slowly cooling ember, no longer generating energy but glowing with residual heat. The star that once might have warmed planets and perhaps nurtured life becomes a dense crystallizing sphere of degenerate matter, slowly fading into cosmic obscurity. Yet even in death, these stars continue to contribute to the cosmic story. The planetary nebulae they create are sites of complex chemistry where molecules form and dust grains condense. The heavy elements they've synthesized and expelled enrich the interstellar medium, increasing the metallicity of future stellar generations. The white dwarfs they leave behind serve as laboratories for extreme physics and as timekeepers for the galaxy's history. For stars born with more than 8 times the mass of our Sun, death comes not gradually but catastrophically in one of the most powerful explosions known in the universe. A core collapse supernova. These massive stars have lived fast, burning through their nuclear fuel in mere millions of years rather than billions, and they die young in spectacular fashion, briefly outshining entire galaxies and forging the heaviest elements in nature. The path to catastrophe begins after the massive star exhausts the helium in its core. Unlike their lower mass cousins, these stars have sufficient mass and core pressure to ignite carbon fusion, reaching the billion-degree temperatures needed for carbon nuclei to overcome their electrical repulsion and fuse. Carbon burning produces neon, sodium, and magnesium, and releases energy that temporarily halts core contraction. But carbon fuel is limited, and at these extreme temperatures, it burns rapidly, perhaps just 1,000 years for a 20 solar mass star. When carbon is exhausted, the core contracts and heats again, reaching temperatures where neon burning begins. The process accelerates relentlessly. Neon burning might last only a few years, oxygen burning a few months, and silicon burning just days. Each stage is shorter than the last, because each successive fuel provides less energy per unit mass, and neutrino losses become increasingly severe at higher temperatures. The star is racing toward disaster, though from the outside it still appears as a luminous supergiant, giving no obvious sign of the crisis building in its core. The structure of a massive star in its final days resembles an onion, with distinct shells of different composition. The iron core sits at the center, surrounded by shells of silicon, oxygen, neon, carbon, helium, and finally hydrogen in the outermost layers. Each shell burns its respective fuel, creating an incredibly complex and unstable structure. The star has become a delicately balanced system of multiple energy sources, any disruption to which could trigger catastrophic collapse. The iron core grows steadily, as silicon burning in the surrounding shell adds more iron peak elements. Iron 56 is special. It has the highest binding energy per nucleon of any nucleus. This means that neither fusing iron into heavier elements, nor splitting it into lighter ones, releases energy. Both processes require energy input. The iron core is thus inert, a dead stellar heart that can only grow larger and denser as more iron accumulates from the silicon-burning shell above. As the iron core grows, it approaches a critical limit, the Chandrasekhar mass, about 1.4 solar masses. This is the maximum mass that can be supported by electron degeneracy pressure, the same quantum mechanical effect that supports white dwarfs. But unlike a white dwarf, which has had billions of years to cool and settle into a stable configuration, the iron core is hot, dense, and growing rapidly. When it exceeds the Chandrasekhar limit, electron degeneracy pressure can no longer support it against gravity. The collapse, when it comes, is breathtakingly swift. The core, roughly the size of Earth but containing more mass than our Sun, collapses to a sphere just 20 kilometers across in less than a second. The density increases by a factor of 100 billion. Matter is compressed beyond the density of atomic nuclei, reaching densities of 400 million tons per cubic centimetre. At these densities, protons and electrons are forced together to form neutrons, releasing a flood of neutrinos in the process. The collapsing core overshoots nuclear density and bounces back, like a compressed spring suddenly released. This core bounce launches a shockwave outward through the star. You might think this shockwave would immediately blow the star apart, but something unexpected happens. As the shock propagates outward through the iron core, it loses energy by photodisintegrating iron nuclei back into helium nuclei and neutrons, essentially undoing millions of years of nuclear fusion in milliseconds. The shock stalls, seemingly unable to escape the star's gravitational pull. For decades, this was one of the great puzzles in astrophysics. Computer simulations showed the shock stalling, yet we observe supernovae, so something must revive it. The solution appears to involve the enormous number of neutrinos produced during core collapse. Though neutrinos rarely interact with matter, the core is so dense and the neutrino flux so intense that a small fraction of the neutrinos deposit their energy behind the stalled shock. This neutrino heating, possibly combined with convective instabilities and rotation, revives the shock and drives the explosion. The explosion that follows is almost incomprehensibly powerful. A typical core collapse supernova releases about 10 to the 46th joules of energy, more energy than our Sun will produce in its entire 10 billion year lifetime, released in just seconds. The explosion is so bright that a single supernova can outshine its entire host galaxy, containing hundreds of billions of stars, for weeks or months. Most of the energy, about 99%, is carried away by neutrinos. These ghostly particles stream out from the collapsed core at the speed of light, carrying information about the extreme physics occurring in the stellar heart. The detection of neutrinos from supernova 1987A in the Large Magellanic Cloud confirmed our basic understanding of core collapse and marked the birth of neutrino astronomy. About 1% of the energy goes into the kinetic energy of the explosion, still an enormous amount, sufficient to accelerate several solar masses of material to speeds of thousands of kilometers per second. The expanding shockwave heats the stellar material to billions of degrees, creating conditions even more extreme than those in the stellar core before collapse. In this incredibly hot, dense environment, a remarkable variety of nuclear reactions occur. The R process, or rapid neutron capture, occurs in the neutrino-driven wind just above the forming neutron star and in the shocked stellar envelope. Unlike the S process in red giants, where neutron captures occur slowly, the R process involves such intense neutron fluxes that nuclei capture many neutrons before having time to decay. This process creates very neutron-rich isotopes that then decay towards stability, producing about half of all elements heavier than iron, including gold, platinum, uranium, and other heavy elements that cannot be made through slow neutron capture. The shock wave also triggers explosive nucleosynthesis as it propagates through the star's outer layers. The sudden heating causes rapid nuclear burning that produces different isotopes than the slow, steady burning during the star's lifetime. Explosive oxygen burning produces silicon, sulfur, argon, and calcium. Explosive silicon burning creates iron peak elements, including titanium, chromium, manganese, iron, cobalt, and nickel. Explosive neon and carbon burning contribute their own unique isotopic signatures. One particularly important product is nickel-56, a radioactive isotope that decays to cobalt-56 and then to iron-56. The decay of nickel-56, with a half-life of 6 days, and cobalt-56, with a half-life of 77 days, powers the optical display of the supernova for months after the explosion. The amount of nickel-56 produced largely determines the peak brightness of the supernova, making it a crucial diagnostic of the explosion mechanism. The explosion ejects the star's envelope into space at tremendous speeds, creating a supernova remnant that will expand for thousands of years. The ejected material, enriched with newly synthesized elements, slams into the surrounding interstellar medium, heating it to millions of degrees and creating a bubble of hot gas that glows in X-rays. These supernova remnants are cosmic particle accelerators, generating high-energy cosmic rays that fill the galaxy. Famous supernova remnants like the Crab Nebula, Cassiopeia A, and the Veil Nebula show us different stages of this expansion and cooling process. The Crab Nebula, from a supernova observed by Chinese astronomers in 1054 AD, is still expanding at over 1,000 kilometers per second, nearly 1,000 years later. These remnants are beautiful and scientifically valuable, allowing us to study the composition of the ejected material and the physics of shock waves in space. Not all of the star is ejected in the explosion. The collapsed core remains as either a neutron star or, for the most massive stars, a black hole. The dividing line between neutron star and black hole formation is not precisely known, but lies somewhere around 20 to 25 solar masses for the initial star, corresponding to a core mass of about 3 solar masses. The exact boundary depends on the equation of state of matter at nuclear densities, one of the great uncertainties in physics. Neutron stars are among the most extreme objects in the universe, with masses between 1.4 and about 2 solar masses compressed into a sphere just 20 kilometers across. They have densities comparable to atomic nuclei. A teaspoon of neutron star material would weigh about 1 billion tons. The surface gravity is 200 billion times Earth's gravity. A human would be instantly crushed to a layer of atoms just micrometers thick. These stellar remnants are called neutron stars because they're composed primarily of neutrons, though they likely have complex internal structures. The outer layers might contain a lattice of heavy nuclei in a sea of electrons and neutrons. Deeper down, matter exists as a superfluid of neutrons with a smaller fraction of protons and electrons. The core might contain exotic matter, hyperons, kaon condensates, or even free quarks. The physics of matter at these densities pushes our understanding to its limits. Many neutron stars are observed as pulsars, emitting regular pulses of radiation as they rotate. The youngest pulsars spin incredibly rapidly. The fastest known pulsar rotates 716 times per second, its surface moving at about 24% of the speed of light. These rapid rotations generate enormous magnetic fields, typically 1 trillion times stronger than Earth's magnetic field. The combination of rapid rotation and strong magnetic fields accelerates particles to near light speed, creating beams of radiation that sweep across space like cosmic lighthouses. For the most massive stars, even neutron degeneracy pressure cannot halt the collapse. The core collapses completely, forming a black hole, a region of space-time where gravity is so strong that nothing, not even light, can escape. The formation of a black hole during a supernova might produce an even more powerful explosion, called a hypernova or a long-duration gamma-ray burst, briefly the brightest electromagnetic event in the universe. Some massive stars might collapse directly to black holes without a successful supernova explosion. These failed supernovae would cause the star to simply disappear, leaving behind a black hole with no fanfare. Recent surveys have found candidate disappearing stars that might represent such events, though confirming their nature is challenging. The death of massive stars plays a crucial role in galactic evolution. Supernovae are the primary source of elements heavier than oxygen in the universe. Every atom of gold in your jewellery, every atom of iodine in your thyroid, every atom of uranium in Earth's core was forged either in the explosive death of a massive star or in the collision of neutron stars. Without supernovae, the universe would contain only hydrogen, helium, and trace amounts of lighter elements. Supernovae also provide mechanical feedback that regulates star formation in galaxies. The energy and momentum injected by supernova explosions heats and stirs the interstellar medium, sometimes triggering new star formation by compressing nearby gas clouds, other times preventing star formation by dispersing gas that would otherwise collapse. This feedback is crucial for understanding why galaxies have the properties we observe. The chemical enrichment from supernovae is not uniform, but creates patterns and gradients in galaxies. Each supernova enriches its local environment, creating pockets of higher metallicity. Over billions of years and countless stellar deaths, galaxies develop metallicity gradients, typically with higher metallicity in their centers, where star formation has been most active. These patterns tell the history of star formation and stellar death across cosmic time. After the dramatic death throes of stars, whether the gentle planetary nebula phase of sun-like stars or the violent supernova explosions of massive stars, what remains are stellar remnants, white dwarfs, neutron stars, and black holes. These objects represent the final chapter in stellar evolution, yet they continue to play active roles in the cosmic drama, influencing their surroundings and sometimes experiencing resurrections or further transformations that can be even more spectacular than their original deaths. White dwarfs, the remnants of low and medium mass stars, begin their afterlives as extraordinarily hot, dense spheres of degenerate matter. A newly formed white dwarf might have a surface temperature exceeding 100,000 degrees, making it one of the hottest objects in the universe, despite being only Earth-sized. This heat is residual thermal energy from the star's previous life, slowly radiating away into space over trillions of years. The cooling process of white dwarfs follows well-understood physics that makes them excellent cosmic chronometers. Initially, the cooling is relatively rapid as the hot surface radiates energy efficiently. A white dwarf might cool from 100,000 degrees to 50,000 degrees in just 100 million years. But as the temperature drops, the cooling rate slows dramatically. Cooling from 20,000 degrees to 10,000 degrees takes about 1 billion years, and further cooling to 5,000 degrees requires several billion years more. As white dwarfs cool, fascinating changes occur in their interiors. When the temperature drops below about 10 million degrees, the carbon and oxygen ions in the core begin to crystallize, forming a solid lattice structure. The white dwarf literally becomes a giant crystal, possibly the largest single crystals in the universe. This crystallization releases latent heat, temporarily slowing the cooling process and extending the white dwarf's visible lifetime by billions of years. The crystallization process might also lead to interesting chemical separation within the white dwarf. Heavier elements like oxygen might settle toward the center, while lighter carbon rises, creating compositional gradients. Some theories suggest that the innermost regions of cool white dwarfs might crystallize into diamond, cubic carbon lattice, just like terrestrial diamond, but on a stellar scale. A typical white dwarf might contain a diamond crystal, the size of Earth, though hidden beneath layers of other materials. The atmospheres of white dwarfs tell fascinating stories about stellar death and sometimes about destroyed planetary systems. Most white dwarfs have pure hydrogen or pure helium atmospheres, as the intense surface gravity causes heavier elements to sink out of sight in just days or weeks. But about 30% of white dwarfs show spectral lines of heavier elements like calcium, magnesium, and iron. These polluted white dwarfs are actively accreting material, probably from disrupted asteroids or planets. When a rocky body ventures too close to a white dwarf, tidal forces tear it apart, creating a debris disk that slowly spirals onto the white dwarf's surface. By studying the composition of this accreted material, astronomers can determine the composition of the destroyed body. This provides a unique opportunity to study the composition of exoplanetary material, revealing that many systems have rocky bodies similar in composition to Earth, while others show more exotic compositions. In binary systems, white dwarfs can experience dramatic resurrections. If a white dwarf has a companion star that evolves and expands, material can flow from the companion onto the white dwarf. This accretion can lead to several different outcomes, depending on the accretion rate and the white dwarf's mass. At low accretion rates, hydrogen builds up on the surface until it explosively fuses in a nova eruption. The white dwarf survives these explosions and can undergo many nova eruptions over millions of years. At higher accretion rates, hydrogen burns steadily on the white dwarf's surface, gradually increasing its mass. If the white dwarf approaches the Chandrasekhar limit of about 1.4 solar masses, carbon fusion can ignite in the core under degenerate conditions. This leads to a thermonuclear runaway that completely disrupts the white dwarf in a Type Ia supernova explosion. These explosions are remarkably uniform, making them excellent standard candles for measuring cosmic distances. The merger of two white dwarfs in a binary system can produce even more exotic outcomes. If the combined mass exceeds the Chandrasekhar limit, the merger might produce a type Ia supernova. But if the merger is gentle enough, it might instead produce a massive, rapidly rotating white dwarf that later collapses to form a neutron star. Some mergers might produce peculiar objects like R Coronae Borealis stars, which show dramatic dimming episodes when carbon dust condenses in their atmospheres. Neutron stars, the remnants of more massive stars, begin their afterlives spinning rapidly and possessing enormous magnetic fields. Young neutron stars, often observed as pulsars, are cosmic laboratories for extreme physics. The conditions in and around neutron stars cannot be replicated in any terrestrial laboratory, making them invaluable for testing our understanding of fundamental physics. The structure of a neutron star is still not fully understood, as it depends on the behavior of matter at densities exceeding nuclear density. The outer layers, perhaps a few meters thick, consist of ordinary atoms, though compressed to densities millions of times greater than any terrestrial material. Below this is the outer crust, where atomic nuclei form a crystalline lattice in a sea of free electrons. The nuclei become increasingly neutron-rich with depth as the density increases. Deeper still is the inner crust, where neutrons begin to drip out of nuclei, forming a superfluid that coexists with the nuclear lattice. The transition to the core occurs at about half nuclear density, where nuclei dissolve entirely into a fluid of neutrons, protons, and electrons. The neutrons likely form a superfluid, while the protons form a superconductor, creating a state of matter unlike anything else in the universe. The innermost core of a neutron star, where densities exceed several times nuclear density, might contain exotic matter. Strange quarks might appear, forming hyperons or even strange quark matter. Some theories suggest the core might undergo a phase transition to deconfined quark matter, essentially a giant quark nugget. These different possibilities would affect the neutron star's maximum mass and its behavior during mergers, making observations of neutron stars crucial for understanding fundamental physics. Pulsars, rapidly rotating neutron stars with strong magnetic fields, show remarkable timing stability, rivaling atomic clocks in precision. The fastest millisecond pulsars, spun up by accretion from companion stars, rotate hundreds of times per second, with periods stable to better than 1 part in 10 to the 15th. This stability allows pulsars to be used for precision tests of general relativity, searches for gravitational waves, and even navigation in space. The magnetic fields of neutron stars, typically 1 trillion times stronger than Earth's field, create extraordinary phenomena. Charged particles, accelerated along magnetic field lines, produce beams of radiation from radio waves to gamma rays. In magnetars, neutron stars with the strongest known magnetic fields, exceeding 10 to the 15 Gauss, the magnetic field energy exceeds the gravitational binding energy. Magnetar flares can release as much energy in a fraction of a second as our Sun emits in thousands of years. Neutron stars in binary systems show remarkable diversity. X-ray binaries occur when a neutron star accretes material from a companion star, heating the infalling material to millions of degrees and producing intense X-ray emission. Some systems show X-ray bursts when accreted hydrogen undergoes explosive fusion on the neutron star surface. Others show quasi-periodic oscillations that probe the innermost regions of the accretion flow just above the neutron star surface. The merger of 2 neutron stars creates one of the most spectacular events in the universe, producing gravitational waves, gamma-ray bursts, and kilonovae. The LIGO and Virgo gravitational wave detectors have observed several neutron star mergers, with GW170811 being the first observed in both gravitational waves and electromagnetic radiation. The merger ejects neutron-rich material that undergoes our process nucleosynthesis, creating heavy elements including gold, platinum, and uranium. The optical and infrared glow from this radioactive decay, called a kilonova, confirms that neutron star mergers are major sources of heavy elements in the universe. Black holes, the remnants of the most massive stars, represent the ultimate stellar endpoints. Once formed, stellar mass black holes between about 5 and 50 solar masses can only grow by accreting material or merging with other compact objects. The event horizon, the boundary beyond which nothing can escape, defines the black hole's size. For a 10 solar mass black hole, the event horizon radius is about 30 kilometers. Despite their reputation as cosmic vacuum cleaners, black holes don't suck in everything around them. A planet orbiting a black hole at the same distance Earth orbits the Sun would feel exactly the same gravitational force as Earth feels from the Sun, only very close to the black hole, within a few times the event horizon radius, do relativistic effects become important. The innermost stable circular orbit, inside which material inevitably spirals into the black hole, is at 3 times the event horizon radius for a non-rotating black hole. When black holes accrete material, they can produce some of the most luminous phenomena in the universe. As material spirals inward through an accretion disk, friction heats it to millions of degrees, causing it to emit intense X-rays. The efficiency of this process can exceed 10%, converting 10% of the rest mass energy into radiation, compared to less than 1% efficiency for nuclear fusion. This makes accreting black holes among the most efficient energy sources in the universe. Jets launched from accreting black holes can extend for thousands of light years, carrying energy and momentum far from the black hole. These jets, powered by magnetic fields threading the accretion disk or the rotating spacetime near the black hole, accelerate particles to nearly the speed of light. In microquasars, stellar mass black holes with jets, we can observe changes in real time that would take millions of years in supermassive black hole systems. The merger of 2 stellar mass black holes produces the strongest gravitational waves in the universe. The LIGO and Virgo detectors have observed dozens of black hole mergers, revealing a population of black holes more massive than expected from stellar evolution models. Some of these black holes might be primordial, formed in the early universe, or might result from stellar mergers or accretion. The final moments of a black hole merger, when the 2 black holes spiral together and merge at a significant fraction of the speed of light, briefly emit more power in gravitational waves than all the stars in the observable universe emit in light. The death of stars, whether gentle or violent, does not mark the end of their contribution to the cosmic story. Instead, it initiates a grand recycling process that enriches the universe with heavy elements, triggers new generations of star formation, and gradually transforms the chemical composition of galaxies over billions of years. This continuous cycle of stellar birth, death, and rebirth is the engine that drives galactic evolution and makes possible the existence of rocky planets and life as we know it. When stars die and expel their enriched material into space, they create a complex, multi-phase interstellar medium. The gas ejected by planetary nebulae is initially hot, around 10,000 degrees, and expanding at tens of kilometers per second. Supernova ejecta is even more extreme, with temperatures of millions of degrees and expansion velocities of thousands of kilometers per second. This hot gas doesn't simply dissipate uniformly, but interacts with existing interstellar material in complex ways. The interstellar medium consists of several distinct phases in rough pressure equilibrium. There's the cold neutral medium, with temperatures around 100 degrees Kelvin, where hydrogen exists as neutral atoms. The warm, neutral medium, at about 8,000 degrees, fills much of the galactic disk. The warm, ionized medium, also at about 8,000 degrees, but ionized by ultraviolet radiation from hot stars, traces star-forming regions. And the hot, ionized medium, at millions of degrees, fills supernova-carved bubbles and chimneys extending into the galactic halo. As stellar ejecta expands into this multiphase medium, it creates shock waves that compress, heat, and accelerate the surrounding gas. These shocks can trigger gravitational instabilities in nearby molecular clouds, causing them to collapse and form new stars. The Orion Nebula, one of the nearest star-forming regions to Earth, may have been triggered by a supernova explosion a few million years ago. The expanding bubble from that ancient explosion compressed nearby gas clouds, initiating the burst of star formation we observe today. The heavy elements produced by stars don't remain as isolated atoms, but quickly engage in complex chemistry. In the cooling gas behind shock waves, atoms collide and form molecules. Simple molecules like molecular hydrogen, carbon monoxide, and water form first, followed by increasingly complex species. Radio telescopes have detected over 200 different molecular species in interstellar space, including organic molecules like formaldehyde, methanol, and even amino acids. Dust grains play a crucial role in this cosmic recycling. Formed in the cooling outflows from red giants and in supernova ejecta, these tiny solid particles, typically less than a micrometer across, serve as catalysts for chemical reactions. Atoms and molecules stick to dust grain surfaces, where they can move around and react more easily than in the gas phase. Water ice, methane, ammonia, and more complex molecules form icy mantles on dust grains, creating the raw materials for planet formation. The journey of elements from stellar death to incorporation in new stars and planets is long and complex. Consider a carbon atom created in the helium-burning core of a red giant 5 billion years ago. That atom was dredged up to the star's surface and expelled in a stellar wind, spending millions of years travelling through space as part of an expanding shell. Eventually, the shell merged with the general interstellar medium, and our carbon atom became part of a diffuse cloud. Over hundreds of millions of years, that cloud was swept up by spiral density waves in the galaxy, compressed and incorporated into a giant molecular cloud. Within that cloud, our carbon atom became part of a carbon monoxide molecule, which helped cool the gas through radiation, allowing it to collapse more efficiently. As a dense core formed and collapsed towards star formation, our carbon atom fell into the accretion disk around a forming star, perhaps our Sun. In the disk, our carbon atom might have been incorporated into a dust grain, which collided and stuck with other grains, gradually building up to pebbles, then boulders, then planetesimals. Through a series of collisions and mergers, it became part of a terrestrial planet. Geological processes might have cycled it between the planet's interior and surface multiple times. Eventually, through volcanic outgassing, it entered the atmosphere as carbon dioxide, was absorbed by ocean water, taken up by photosynthetic organisms, and incorporated into organic molecules. That carbon atom, forged in a star that died before our Sun was born, might now be part of the DNA in your cells. This is not just a fanciful story, but the actual history of much of the material in our bodies and our planet. Spectroscopic observations of stars of different ages show how the galaxy's composition has evolved over time. The oldest stars in our galaxy's halo have heavy element abundances less than 1,000th of the Sun's. These ancient stars formed from nearly pristine hydrogen and helium left over from the Big Bang. Each subsequent generation of stars has higher metallicity as the cumulative effect of stellar nucleosynthesis enriches the interstellar medium. The rate of enrichment depends on the star formation history and the initial mass function, the distribution of stellar masses when stars form. Massive stars, though rare, contribute disproportionately to enrichment because they produce more heavy elements and die quickly, returning enriched material to the interstellar medium in just millions of years. Low-mass stars lock up material for billions of years before returning it to space, creating a delay in the enrichment process. Different elements are produced on different timescales, creating distinctive patterns in galactic chemical evolution. Oxygen and other alpha elements, those made from helium nuclei, are produced primarily in massive stars and released in core collapse supernovae on short timescales. Iron is produced by both core collapse supernovae and type Ia supernovae, but type Ia supernovae have a delay time of at least 100 million years and possibly billions of years. This creates a characteristic pattern where young stellar populations are enhanced in alpha elements relative to iron compared to older populations. The spatial distribution of enrichment is also complex. Supernovae don't enrich space uniformly, but create pockets of enhanced metallicity. Stellar winds from clusters of massive stars create bubbles of hot, enriched gas. These bubbles can break out of the galactic disk entirely, creating galactic fountains that transport enriched material into the halo, where it cools and rains back down onto the disk. This circulation helps spread heavy elements throughout the galaxy, though gradients persist with higher metallicity in galaxy centers where star formation is most intense. In galaxy clusters, an additional enrichment process operates. Supernova-driven winds and active galactic nuclei can expel enriched gas from galaxies entirely, polluting the intergalactic medium. Ram pressure stripping as galaxies move through the cluster medium can also remove enriched gas. This gas, heated to millions of degrees, fills the space between galaxies and contains a substantial fraction of all the heavy elements ever produced. X-ray observations of galaxy clusters reveal this hot, enriched plasma, glowing with emission lines from highly ionized iron, oxygen, and other elements. The efficiency of star formation and stellar feedback creates a delicate balance that regulates galactic evolution. If star formation is too efficient, galaxies would quickly convert all their gas to stars, producing intense bursts of supernova that would blow out all remaining gas, ending further star formation. If stellar feedback is too strong from the start, it prevents gas from cooling and forming stars at all. The observed properties of galaxies suggest they live in a sweet spot where star formation and feedback are balanced, allowing steady star formation over billions of years. This balance can be disrupted by galactic interactions. When galaxies collide or pass close to each other, gravitational tides can funnel gas toward galaxy centers, triggering intense starbursts. These events can increase star formation rates by factors of hundreds, rapidly converting gas to stars and producing spectacular supernova fireworks. The remnants of these starbursts are visible as populations of star clusters with similar ages, marking ancient episodes of intense star formation. The cosmic recycling process connects the smallest and largest scales in the universe. Nuclear reactions occurring in spaces smaller than an atomic nucleus in stellar cores ultimately affect the evolution of entire galaxies. The carbon in your pencil, the oxygen you breathe, the iron in your blood, all were forged in stars that lived and died before our solar system formed. We are literally made of star stuff, assembled from atoms that have been recycled through multiple generations of stars over billions of years. This recycling is not perfectly efficient. Some material is locked up permanently in stellar remnants, white dwarfs, neutron stars, and black holes. Some is ejected from galaxies entirely, enriching the intergalactic medium but becoming unavailable for future star formation. Some falls into supermassive black holes at galaxy centers. Over cosmic time, the rate of star formation decreases as gas is consumed, ejected, or locked away. The universe is slowly winding down, though the process will take trillions of years to complete. Currently, we live in an interesting epoch of cosmic history. The universe is about 13.8 billion years old, and star formation peaked about 10 billion years ago. The rate of star formation has been declining since then, and will continue to decline. Heavy element production peaked a few billion years ago and is also declining. We exist at a time when the universe has been sufficiently enriched to allow the formation of terrestrial planets and life, but star formation is still active enough to create new planetary systems. Earlier in cosmic history, there weren't enough heavy elements. Far in the future, star formation will be a rare event. The study of stellar populations in our own and other galaxies reveals this history. Globular clusters, dense collections of hundreds of thousands of stars, show evidence of multiple populations with different chemical compositions, suggesting self-enrichment from the first generation of stars. The galactic bulge contains old, metal-rich stars, evidence of an intense burst of star formation early in the galaxy's history. The thin disk shows a clear age metallicity relationship, with younger stars having higher metallicity, recording the gradual enrichment over billions of years. Dwarf galaxies, with their lower masses and shallower gravitational potential wells, show different enrichment patterns. They lose enriched gas more easily to supernova-driven winds, leading to lower overall metallicity and larger scatter in element abundances. Some dwarf galaxies show evidence of episodic star formation, with bursts separated by quiet periods when gas was expelled and had to be reacquired. These small galaxies serve as laboratories for understanding stellar feedback and chemical evolution in simple systems. The future of cosmic recycling depends on several factors. Dark energy is accelerating the universe's expansion, which will eventually isolate galaxies and galaxy groups from each other, cutting off any external gas supply. Star formation will continue using recycled material, but the overall rate will decline. Low-mass stars will become increasingly common as the metallicity increases, since metal-rich gas clouds fragment more easily into small pieces. The final generation of stars, forming trillions of years from now, might consist entirely of brown dwarfs and low-mass red dwarfs. Even after star formation ceases, stellar collisions in dense environments like globular clusters can create new stars from the merger of stellar remnants. White dwarf mergers might produce new helium-burning stars. Neutron star collisions will continue to produce heavy elements through our process nucleosynthesis. These processes will become increasingly important in the far future when conventional star formation has ended.